So section 2 of chapter 3 is the atomic structure. So there are two main parts to the atom, the nucleus and the electron cloud. So the nucleus is this small region at the very center of the atom, and it contains protons and neutrons, which we'll talk more about later. Those are subatomic particles. Overall, the nucleus has a positive charge because protons have a positive charge, and neutrons are neutral with no charge. So the positivity wins out. The other part of the atom is the electron cloud, and you can abbreviate electron with E and the little negative sign. It's this outer section. It's very, very large and very open. It looks like there's rings like a hula hoop, but they are not actually there. The electrons just rotate in the circular pattern. It's just a visual to help you understand. So just a comparison for you. If the nucleus was the size of a marble, then the electron cloud is the size of a football field. So I know the picture doesn't do justice, but you're talking about something very small in the nucleus to something very large in the electron cloud. And the electron cloud contains electrons, which are negative, so the electron cloud is overall negative. So looking at these discoveries of these subatomic particles, the electron was discovered in 1897 by J.J. Thomson. He basically thought or said, atoms are electronically neutral, meaning atoms do not have a charge. So there must be a negative charge to balance out the positive charge of a proton. So going back to the previous picture, we said that the nucleus is positive, the surrounding electron cloud is negative. Positive and negative cancel out, so the atom as a whole is neutral. So he's saying that he knew there was positivity here, and he knew the atom was neutral, so he theorized there must be something negative within the atom to cancel the positivity out. And he was obviously correct. So he used the cathode ray tube to discover his electron. I'm going to skip the video. I'll just explain it to you. Okay, so this is what the cathode ray tube looked like. It's a glass tube. It's connected to electrical outlets, a cathode and an anode. And then they shot through particles. And the goal was to get the particles to hit the end of the tube and fluoresce or light up. This is just another picture of it. So they thought this was going to happen. They would go straight through. This is what actually happened. The negative particles they were shooting through were bending downwards to the positive electrical field. So negative was attracting to positive. So here's what Thomson realized. The cathode ray, which is what he was shooting in here, these little particles, must have negative charges in them because they were attracted to the positive electrical field. And we know that opposites attract. They were also repelled by the negative field. None of them were going towards it. So his model of the atom is called a plum pudding model. And this is what plum pudding looks like. It's not pudding like we think of. It's almost like a fruit bread or cake. It's a European thing. So Thomson proposed that positive atoms contained negative electrons. And he thought these negative electrons were randomly placed. So this is what he thought the atom looked like. So this purple part is all positive. Think of it like a cookie. And then the electrons were randomly placed negative, like chocolate chips. So they call it the plum pudding model because plum pudding is the bread and then randomly placed fruit bits. Okay, so after the discovery of the electron, Ernest Rutherford discovered the nucleus and officially the proton in 1911. So he used the gold foil experiment to discover the nucleus and in turn the proton officially. So he expected these alpha particles, which he was shooting through this gold foil, they were positive, to go straight through the gold foil and then hit the opposite side of this detector and once again light up. And gold foil is just like aluminum foil, but made of gold. Gold is non-reactive. That's why he used it. He did observe that some of the alpha particles did go straight through, and they hit the opposite side. But other particles were deflected, so he could see where they were lighting up at on the screen as to where they ended up. And some of them even were deflected backwards. So this is what he expected his results to look like. This is the alpha sign. Kind of looks like a fish without the tail connected. They were positive. He shot the alpha particles through the gold foil, and he thought they would continue straight through the gold foil and light up right across on the detector. So something like this. And using the plum pudding model, it makes sense because they should have just gone straight through and not really hit anything. Here's what the actual results were. They shot the alpha particles through. Some of them went straight across, but most of them were deflected in other directions, and some even came straight back and didn't even go through the foil. So something like this. So yeah, a lot of them were going straight through, but something was causing them to deflect the direction or come back. And just another picture showing that. So Rutherford came up with 3 conclusions. He said there must be something powerful in the center of the atom, which we now call the nucleus, because it was forcing these alpha particles in different directions. He said it must be small, though, because only some alpha particles hit and were deflected. And he said it must also be positive, because if the alpha particles that were positive hit and then were repelled away from it, positive and positive repel. If they were negative, they would have stuck to it. So he basically suggested that there was a negative electron distributed way outside, and the actual nucleus was very small. That was that powerful central positive charge force. And if you go back to the picture, the light blue is representing the electron cloud. The dark blue is representing the nucleus. Look at the size comparison. It is very small. So only some are going to hit off it and be deflected. The rest should be able to go through straight. So his conclusions made sense. Okay, so that was his. And Rutherford's model just looks like this. The nucleus is in the very center, and the outside surrounding area is the electrons, just kind of randomly placed. So now we have discovery of the neutron by James Chadwick in 1932. We're not going to get into a lot of details about this one because it's very complex. Just understand that he's scattering data. So he scattered all these different particles, alpha particles, neutral particles, protons, and made a discovery. We'll leave it at that. So now that we know that these atomic particles were discovered, let's talk about the actual composition of the atom and the nucleus. So the proton is positively charged, P for proton, P for positive. It has a pretty small mass, so negative 27. There's 26 zeros before this number. The neutron is neutral, it doesn't have a charge, and its mass is a little bit bigger, but not by much. Pretty comparable. These are both found inside the nucleus. So the positive proton dominates because neutron is neutral, so the nucleus is positive. Electrons are negatively charged, and we like to say they're almost massless. We know from chapter 1 they can't be massless because then they wouldn't exist. But they're very, very, very small compared to the neutron and proton. And these are found in the electron cloud. So if they have a negative charge and the atom's nucleus has positive charge, positive and negative cancel out, the atom is neutral. As far as looking at the weights, like I said, neutron and proton are pretty even, but this is just a visual of how many electrons you would need to equal 1 proton. So the electron is very small compared to the proton and neutron. So this is just a 2D model of our current atom. Neutrons and protons. Neutrons are black. I don't know what the screen is. Protons are red, positive, and the electrons are outside, floating around. If you make a 3D model, it looks like this. So I said these rings don't actually exist. They're not like hula hoops, but the atoms will circle this way, and then the other atoms will circle this way, or electrons, sorry, and that way they won't collide. So just comparing, Dalton's model was just a circle. He just thought there was stuff there, but it couldn't be explained. Thomson's was the plum pudding. So he had positivity throughout the gray and then negatively randomly dispersed. Rutherford's started to get a little bit better. He knew the electrons were outside of the nucleus, and he knew that the nucleus was centralized and small. We don't talk about Bohr, but Bohr kind of figured out, well, we will talk about him next chapter. Bohr figured out a very specific electron configuration structure. So he built on Rutherford's. We're not going to talk about this one at all because that's really complex. It's for quantum mechanics. And then Chadwick discovered those neutrons, so we were able to add neutrons to the nucleus with protons. Just another example, like I said, Dalton's, didn't know a lot. Thomson's, Rutherford's, Bohr's, which is the most common we talk about, and this is for quantum. All right, and that's it for 3.2.